The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees.
All right, thank you all for attending. The first presentation sort of gave a broad scope of most of the situations you'll encounter with strengthening masonry walls with FRP. This one is going to look a little bit more focused on infill walls. So when we're talking about infill walls, you can see that we're dealing with typically a reinforced concrete frame, and the focus of this research was related to out-of-plane loading. For a typical infill wall, you might have a flexural failure of an unstrengthened wall in which you have a crack develop at mid-height. To strengthen against this type of failure, especially for extreme loading, you might use FRP sheets. These could be oriented in various ways, typically externally bonded or near-surface mounted. However, one of the things that we observed in a previous experimental program with strengthening infill walls was a premature failure in shear sliding. So in this case, the wall itself was more or less intact, however, it slid out from the reinforced concrete frame in something akin to a rigid body fashion. So to enhance the strength and really utilize more of the FRP, one approach would be to simply overlap the FRP reinforcement onto the surrounding frame. Again, here we have a premature failure in which the wall begins to slide and debonds the FRP from the reinforced concrete frame. If you really need a tremendous amount of strength, you could go with a steel shear restraint anchorage. This one basically is designed to prevent the shear sliding around the perimeter of the wall. So your FRP strengthens the wall and then the steel strengthens the boundary. The disadvantage of this approach is pretty obvious. It's somewhat bulky and doesn't sort of fit in with the advantages of using a lightweight FRP material, but it is one option. So the focus of the current research that we're working on is to really dive into the end anchorage for the FRP materials and develop some recommendations for designers to use in this application. So we'll start with the experimental program. We simplified the behavior to a one-way span to really isolate the effect of the anchorage. You can see the strengthening there, and this specimen is shown overlapping. We looked at different end anchorage types. So from the control specimen, we want to see, does the FRP do anything? So we considered the unstrengthened case. We considered a case with overlap, one with steel shear restraints, in this case, plates at the top and bottom. The fourth case was an embedded bar, so this would be a groove that was cut at the top and bottom, and then you have an FRP bar that's inserted, and then the main FRP strengthening is wrapped around that bar. And then the last case would be the FRP anchors that some of you may be familiar with. Basically, they're drilled into the reinforced concrete frame and then impregnated with epoxy at the same time that you would have the strengthening of the main FRP. We considered several different FRP types, including glass and carbon fibers, as well as a PET, which some of you may be interested in. This one has a relatively low modulus elasticity, but a very large rupture strain. So the test setup we basically used a strong wall and an airbag, and we applied a uniformly distributed pressure to the wall until failure. This is what we observed for the specimens with overlap. You can see again we have the sliding of the wall out of the frame. This begins to initiate debonding, and that debonding then begins to creep up the wall or the overlap region until you have a loss of strength. When you have FRP anchors, again you have sliding, again you have debonding, but in this case the FRP debonds up to the level of the anchors, and then the strength of the system is governed by the anchors themselves. In this case, the pull-out or rupture of the anchor. And then finally, the shear restraint case. This was the one where we were able to develop the full strength of the FRP material in tension. We had FRP rupture for the case of glass, and then we had extremely large deflections develop in the PET system. So it may not be a surprise that strengthening can increase your capacity for out-of-plane loads. You can see this is a load deflection curve. At the bottom we have the control specimen providing FRP strengthening with some overlap, which would be the most basic form of anchorage. You can get a very significant increase in strength. However, when you provide additional anchorage beyond that, you can get a very dramatic increase as well, up to the strength of the shear restraint specimen. So you can see without the additional anchorage, you're not really achieving the full capacity the FRP has to provide. And this graph just shows the difference between the two FRP types for the various anchorage cases. You can see for the GFRP material, which has a higher modulus and lower rupture strain, was able to develop somewhat higher strength relative to PET, which had greater ductility. So next I'd like to talk a little bit about the rational approach and how you might try to design one of these. So the arching mechanism, which was presented earlier, in this case, when we introduce the FRP, we have, in addition to the compression force at the top and bottom of this upper half of the wall, we now have this tension force at midspan from the FRP, which can contribute to the strength as well. So if we apply that methodology, which I haven't given you all the equations, but it's presented elsewhere, you can see that if we apply it to the walls in our experimental program, it provides a pretty good prediction of the predicted failure pressure compared to the measured failure pressure. However, for the walls that fail due to the premature failure mechanisms, it gives unconservative results. And therefore, we wanted to develop several other approaches, depending on the type of anchorage you have, that can account for the potentially premature failure modes. If we zoom in on the anchorage region, prior to cracking, this would be a wall that does not have overlap of the FRP onto the reinforced concrete frame. Prior to cracking, you would have some shear resistance due to cohesion. After cracking, the area of the mortar joint that's in contact with the reinforced concrete frame is significantly reduced. However, you also can develop a thrust force that can provide a frictional resistance at that joint. So if we make a few assumptions here regarding the reduction of the area that's affected for cohesion, and then we provide some sort of guidance about how do we estimate that thrust force based on the geometry of the wall. Using force equilibrium, we can develop an equation that estimates the sliding shear pressure at failure. The only unknown here is this thrust force factor, which relates the height to thickness ratio of the wall and the reinforcement ratio of the FRP to an expected thrust force. So if we provide overlap of the FRP onto the reinforced concrete frame, we allow that wall to slide, debonding the FRP, and now you're introducing a dowel force provided by the FRP. That's the PD you see at the top of this graph. The cohesion term is gone. However, that is now replaced by an FRP dowel force. You can see that that force depends on the geometry of the FRP and material properties, as well as the bond characteristics. In addition, you have a thrust force factor for this condition as well that is slightly different from the previous case due to the additional deformation that has taken place. And similarly, you can resolve that into an equation that can predict the debonding pressure. Finally, when you have an anchorage failure, in this case now the FRP has completely debonded up to the level of the anchor. There is the possibility of a thrust force in this case as well. However, based on the experimental results we had and the geometry that we were using, it was conservative to ignore that thrust force. As a result of the deformation that had taken place, the thrust force was greatly reduced by the time the debonding reached the level of the anchors. You can then determine the anchor capacity. I won't get into all the equations there, but it's related to the embedment depth of the anchors, compression strength, and then the material properties of the anchor itself. Ultimately then, this applied pressure would be related just to the anchor capacity itself. So if you had a wall with no overlap, you would use the shear sliding pressure and the arching pressure to determine what your ultimate capacity would be. Similarly, for walls with overlap, the shear sliding term is replaced by the debonding. And then if you have anchors, you could use the strength of the anchor to determine the capacity. When we use this design approach and compare it to the experimental results, you can see that the prediction is relatively good and that the result is conservative, even for walls failing in the premature mechanisms. Given the brittle nature of many of the failure modes involved, we would recommend a phi factor of 0.6 for all of the various limit states that are considered in the program. So from a design perspective, you're really using the arching mechanism with the FRP strengthening to determine your FRP design. And then once you have your FRP design in place and you know what your load demands are, you would then design or calculate what type of anchorage you need to provide in order to correctly determine the capacity of the infill wall. These are just a few of the references that we utilized.